Okay.
Further ado, unordered tuples in quantum computation, please.
Thank you. Thank you for having me. So my name is Bas Westerbaan, and this is joint work with Bas Westerbaan. He's sitting over there. And so, what did we do? Well, we computed the algebras for several unordered quantum types. So, this was already done. They were already described, but not computed concretely. Well, the difference will become clear. And how did we do it? We used the representation theory of finite groups. I have to thank, Sam Staten just walked out, but I have to thank him because after discussion with him about the paper of Pagani, Peter and Valero, we got this idea to try and do this. Okay, so let's representation theory of finite group. That's quite an old topic, classical topic of mathematics, and it's around 1920s, 1930s. And the important parts of it, which we use for this paper, are by Schur and Weil. So we tried to make our paper easy to read if you don't know representation theory of finite groups. So I hope you find it an easy read then. And if you already know it, I hope you find it an enjoyable read because it's a nice application. Unfortunately, I cannot give a nice introduction to the representation theory of finite groups in such a short talk, but I'll try to give some, try to get you interested in it. Okay, so let's start with something we already know. So what are the algebras for some well-known quantum types? So a qubit, that's 2 by 2 square matrices. And a bit, you can also do that if you're doing algebras, that's c squared. And if I have a pair of bits, and it's important, it's ordered, one comes after the other, it's the tensor, so C4. And you take the tensor as well for the qubits, and you get M2 tensor M2 is M4. Okay, what's an unordered pair of bits? Well, that's C3. Why? It's 0, 0, 1, 1, or 1, 0, which is identified with 0, 1. But what about an unordered pair of qubits? Well, that's what I'm going to answer. I ask a physicist first, and well, better asks if something is already done, right? So, and he replied this: what are you using for your qubits? Are you using fermions or bosons? He continued: if you're using bosons, then it's then it's like with the bits, then it's 0, 0, 1, 1, and the identified ones. But if you're using fermions, he taught me, then it's different. Then it's just C. It's one-dimensional, because if one particle is a 0, then the other must be 1. So okay, so this isn't quite, and he coined the term Pauli exclusion principle there. So this, for computer scientists, this isn't really satisfying, right? Because, well, our type shouldn't depend on the implementation, right? Maybe we don't use particles for qubit, for several separate particles for separate qubits, but maybe use one particle for several qubits. And we also want to have a rule, right? So what's our reflex as computer scientists? Well, what about the co-equalizer of keeping the 2 qubits fixed and the map that swaps the 2 qubits? If there is a type of unordered qubits, if it isn't a co-equalizer, then it would be odd. So what's the rule for the co-equalizer? That's nice. It's if you have any program that takes an unordered pair, then that should correspond exactly to a program which takes an ordered pair but is invariant on the swapping. Okay, right. So you can compute this. That's not too hard to do. The co-equalizer, and it turned out to be M3 plus C. So bosons and fermions. Okay, I have to be a bit more precise because co-equalizer, what category? Well, in finite dimensional C-star algebras with the usual maps in the opposite direction, and if you don't, and if you like, that's the same as using Salinger's Q or CPMS. And as I said, the left part is the boson, so that's what you might expect first time, and the other ones is for the fermions. And you would say, well, is this a symmetric state? Because if you swap it, you get a minus sign. but then you remind that it's the same up to global phase. So, how to show this? Well, the co-equalizer is not too hard to work out, because it maps in the opposite direction. It's an equalizer of algebras, and I hope you forgive me if I use co-equalizer and equalizer interchangeably. And this equalizer of algebras is quite easy to work out. It's just the elements which are invariant in the swapping. And, okay, why is this M3 plus C? Okay, it's not too hard. It's a half of a page of elementary algebra. And when we work this out, and not only for this one, but also for different cases, unordered triple, using qubits instead of qubits, we noticed that we were using stuff from representation theory. So then we tried to apply representation theory, and it worked out really beautifully, easily. So to talk, the rest of the talk is, so first I'll tell the unordered tuples, the general result for unordered tuples, and I'll sketch the proof. Then I'll show two different applications for cycles and unordered words. Okay, so unordered tuples. Well, we also have a decomposition into matrix algebras. By the way, just as in the previous example, we not only have a decomposition into matrix algebras, but also isomorphism, which also says what is it. Okay, so I have to explain I have to explain these letters here. So, how many of these factors are there? What are these lambdas? And which matrix algebras are there? What are the dimensions? So, these two are well-known things from representation theory. And if you haven't seen it, well, don't feel bad about it, but I'll include the definition for completeness. The lambdas are the Young diagrams, the n-block Young diagrams of height at most d, and m lambda is the dimension of the corresponding representation of GLD, or explicitly, you can write it like this. And it's quite easy to compute with. So, as a few examples, an unordered triple of qubits. So, three parts. This is the bosons part, this is the fermions part, but there's another thing in between, which is a bit non-standard. So someone told me that it's like parastatistics, but I don't know anything about it. Another pair of q-quads, then is just fermions and bosons. And another quad of qubits. Then we have three factors, and it's nice to note that here, this is bosonic, and these two are the non-standard in-betweens. And the fermions aren't there because if you have 4 qubits, then you cannot have 4 different values using only 0 and 1. And you can write a script to do it for even more. So this is for, so with 5, tuples with 5 things, unordered, and then these are the dimensions of the systems we use. By the way, these are our own diagrams, so that's nice. So, let me sketch the proof. So first setup. So this is the Hilbert space for n ordered qubits. ISO. And the permutation group of n elements acts on it in a natural way by permuting the tensor factors. So this is on the Hilbert space, and then I can also give an action on the algebra, the bounded operators on it, by this formula. First apply the permutation, then the operator, and then the other way around. And what we want to do is to compute the equalizer of all these actions. Well, equalizers are normally only for 2 maps, but you can do it for several maps at once by repeating. That's not too difficult. And again, because it's an algebra, the equalizer is quite easy to work out. It are all of those matrices which are invariant under the permutation, under the action. Okay, now the crucial observation that makes it all work. That is, here we have the equalizer. So that is what we should think are the unordered tuples. And if we look at it, so this is it in the algebra, if you work it out, then this is all the matrices, the linear maps from H to H that commute with that group action. And that's precisely what is defined as morphisms of representations, or intertwiners, as it's known in that field. Now, that's great, and now the rest is representation theory. Okay, so I need to tell two things about representation theory. First, what is an irreducible representation? If I have a representation on the... Oh, I didn't even say what representation is. A representation is so I have a group and a homomorphism to the endomorphism of a Hilbert space. So the example of a representation here is H, because the symmetric group acts on H. There's a homomorphism from the symmetric group to the endomorphisms of this Hilbert space. So if I have a representation on V of a group and I have a representation on W of a group, then I can look at the direct sum of the vector spaces, and there's an obvious action representation on that direct sum. So a representation can be of this form, or maybe it's not, and if it's not of this form, it's called irreducible. And a basic fact is that every representation splits into irreducible representations. Some irreducible representations, and the same irreducible representation can occur several times. So here I write H as the direct sum over its distinct irreducible representations, and m lambda is the number of times it occurs. So that's one fact I need. And the other one I need is Schur's lemma, which says that the representation homomorphisms between irreducible representations are really simple. If they are distinct, there isn't any. So if you have two distinct irreducible representations, there isn't any map. And if they are the same, then it's only lambda times the identity. So it's the same number as the complex number. And that's really all we need to get it started. Because I look at the equalizer again, so these are the algebra of the unordered tuples. I write out that H is equal to the direct sum of its irreducible representations. I pull out the byproduct, and here I see its representation between irreducible representations. Now, then I can use Schur's lemma, and I see that it's matrix algebras with multiplicities exactly, with dimensions exactly the multiplicities of irreducible representations. Now that's great. But what are the irreducible representations? And what are the multiplicities? Well, this has been worked out by Schur and Weil, and that's called Schur-Weil duality. So that gives us also these formulas on a few slides back. So, okay, so that's what I wanted to say about unordered tuples. But we can also apply it for some different non-unordered types. So, for instance, cycles. So what's classically a cycle? It's like a necklace with colors, with two colors. A 3-cycle is a necklace with 3 beads and 2 colors. And and then you have 4 possibilities. You have 0, 0, 0. You have this one, and then the equal sets are when you cycle it, and then another and another. But what about the 3-cycle of qubits? Again, the obvious thing to do is computing the co-equalizer, but then of the action of the cyclic group of 3 elements. And again, we get non-standard terms. So the M4 here is like the standard one. The 3-cycle of bits was 4 bit. And here we have 2 non-standard ones. So the first one is what you would expect. And the second one is non-standard, and here you have the third root of unity in here. If you cycle it, then you will get the same thing back again, but then multiplied by third root of unity, which is again a global phase we can ignore. And then you can also do it with the thing swapped here. That's the last one. Okay. So how to do this in general? Sure, while doesn't apply to give us the multiplicities or the irreducible representations, but the representation theory of finite groups has other tools to do this, and in this case, it's you just compute the character table. So I don't have time to tell you about it. We gave an introduction to it in our paper, but it's already very well known. And then you can derive the following formula. So this is the multiplicity. So it's a sum of matrices indexed by k, and these are the dimensions of the matrices. Great. You might object that this is an integer, but here's a transcendental number. Maybe you don't like this. So we thought maybe it's easier to compute if we have only fractions. And you can use some number theory, Ramanujan sums and such. And you can get a, well, not that much easier expression, but at least it's all fractions. So a referee asked us, so what's the use of quantum cycles? And I don't know. I tried to look at we tried to figure out a protocol maybe to do something with it, but we couldn't think of something, unfortunately. But here it's in the paper it's a great example of how to compute it if you don't have this nice symmetric group. Okay. Let's see the time. How much time do I have left?
Well, given the little bit of a late start, if you want questions, 2 minutes. If you don't want questions, a bit more.
Okay, then I'll just show the result. Unordered words, you will get, you can compute it's this, and I want to mention that this is like the algebra for ordered words, for ordered words. So that's the Fock space, the Bosonic Fock space. And then you get all the non-standard algebras from the other ones. But interesting enough, we don't get the fermionic Fock space. Okay, so to recap, algebras for unordered types are given by the code classes. That's nothing new, but it's nice to say again. They are more interesting than expected. And it's with the representation theory of finite groups, it's really fun and easy to work out. Thank you.
Questions?
So when you have this unordered pair of qubits, so it has these two components, right?
Yes.
So it's a direct sum. So physically this means that you can measure it to determine which of the two components you're in without actually disturbing the state. What does that actually mean? What does that mean about tuples?
Well, you could have because you have algebras, you can have mixed states, right? So
yeah. Well, all the states you were talking about were mixed, right?
yes. Oh, yeah, well, the typical states are called aberrant mixed, but yeah. So maybe I don't understand your question correctly.
Yeah. I was just wondering what one could do with such a tuple, because if it's a direct sum, that means you can measure it to figure out if you're in the bosonic or the fermionic component, right? You should be able to. Should be sort
yes.
of.
But then you are already in a component. If you have a state on it, then it's already a convex combination of a state on the left.
Right, that's the point. So you can't be in a superposition of being a.
No.
Being a fermion
exactly.
The
Yeah.
physicist here is having trouble with that concept of superposing fermions and bosons.
Exactly.
But it's a probabilistic superposition. It's not a quantum superposition.
Right. Sorry. Next question.
Yeah, let's try at the front there.
Yeah, so I don't know if this is going to be a helpful protocol, but like in a lot of these algebraic black box algorithms, the first thing you do is put some group structure on your computational basis. And so, is there any reason your construction wouldn't work for just some arbitrary group, and then you just find the representation?
Yes, so the point is how to compute this all works. Yes, representation theory is made for this stuff.
So I think, anyway, we can talk about that, but I think it would generally be useful if you're trying to do some algorithm where the first thing you do is put some group structure on it, and there's tons of this.
Yeah.
Lots of this.
There's
lots.
Okay, so let's take Jamie next.
You don't seem to be consistent between saying equalizer or co-equalizer throughout your talk.
Yes, sorry.
And you said something at the beginning about how they're sort of the same, but they're not really the same, are they?
So if you think about programs, then it's a co-equalizer. But if you start computing, then the arrows flip around because you're dealing with predicate transformers, and then it's equalizers.
Right, but they're not equivalent categories in this case.
Well, it's a self-dual category.
The opposite category is
Self-dual category?
So it's contrary and the equivalent to its opposite.
So what was the category in which you were living again?
Cylinder's cube.
I thought you were taking unital maps.
Subunital. So I didn't want to say that the equalizer and the co-equalizer are the same. When I said equalizer, I meant it in one category, and when I said co-equalizer, I meant it in the opposite category.
Okay.
Sorry for confusing you.
So we'll take on the web.
Sorry, can I speak up a bit?
That my comment is related with the comment of the professor, because I think if you can make this decomposition, you can make a tomography scheme for naturally state. Like, but I think you have to take, because these are atoms, right? Each one of the parts of the decomposition is an atom, right?
Yeah, it's our particles.
So they have identity. All of them have identity.
Yes.
So I think you have
Maybe we should talk after the.
yeah.